Count out 3 moles of water for me. You can't. The particles are too small to see and too many to count. 6.022 times 10 to the 23rd of them in a single mole. So chemists never count. They weigh. A mole is a counting word exactly like a dozen. A dozen is 12 of anything. A mole is 6.022 times 10 to the 23rd of anything. Atoms, molecules, ions. 1 mole of water and 1 mole of salt hold the very same number of particles. They just don't weigh the same. Molar mass is the mass, in grams, of 1 mole of a substance, and it's already printed on the periodic table. Oxygen's atomic mass is 16, so 1 mole of oxygen atoms weighs 16 grams. For a compound, add up every atom in the formula. Water is 2 hydrogens at 1.008 plus 1 oxygen at 16, 18.02 grams per mole. So, 3 moles of water. How many grams? Multiply by the molar mass. 3.00 moles times 18.02 grams per mole. Moles cancel, and you're left with grams, 54.1 grams. Moles to grams, multiply. Now run it backwards, 90.1 grams of water. How many moles? Divide by the molar mass, or flip the conversion factor. Grams cancel, and you get 5.00 moles. 1 bridge, 2 directions, moles to grams, multiply. Grams to moles, divide. And the molar mass changes with the formula. Salt is 58.44, carbon dioxide is 44.01. Find the formula first, then build the bridge. Every molar mass in this series came from the same 3 steps, and all you need is a periodic table. Here's nitrogen. The number under the symbol, 14.007, is its atomic mass. It means 1 mole of nitrogen atoms weighs 14.007 grams. For a compound, count every atom in the formula, multiply each one by its atomic mass, and add. Now the step everyone drops. Ammonia is NH3. If you just add nitrogen and hydrogen, you get 15.02. That's wrong. The little 3 is a multiplier. There are 3 hydrogens in there, not 1. So it's 14.007 plus 3 times 1.008. 17.008. 17.03 grams per mole. The subscript is not decoration. Let's do the airbag compound from part 4, sodium azide, NaN3. 1 sodium, 22.99. 3 nitrogens, so 3 times 14.007, which is 42.02. Add them, and you get 65.01 grams per mole. That is exactly the number we use to work out how much nitrogen gas fills the bag. One more rule. When a formula has parentheses, the subscript outside multiplies everything inside. Calcium nitrate is Ca, then NO3 in brackets, subscript 2. That 2 does not just apply to the oxygen, it copies the whole nitrate group. So work out 1 nitrate first. 14.007 plus 3 oxygens is 62.00. Then double it and add the calcium. 164.09 grams per mole. So, 3 steps every time, count the atoms, subscripts included, multiply each one by its atomic mass. Add them up. That's how we got 18.02 for water, 17.03 for ammonia, and 65.01 for sodium azide. Every molar mass in this whole series. Get this step right, and the rest of stoichiometry is just multiplication. Nitrogen plus hydrogen makes ammonia, the reaction behind the fertilizer that grows about half the world's food. Here's the question. You start with 42.0 grams of nitrogen. How many grams of ammonia can you make? The coefficient says 2, so double it? 84 grams? No, grams can't cross that arrow. The coefficients are a ratio of particles. One nitrogen molecule reacts with 3 hydrogen molecules to make 2 ammonia molecules. But those particles don't weigh the same. Weigh them and you get 28 grams, 6 grams, 34 grams, nowhere near 1 to 3 to 2. The ratio only works in moles. So here's the roadmap, and it never changes. Start at grams, divide by molar mass to get down to moles. That's the bridge you already know. Then use the coefficients as a mole ratio to cross the arrow. Then multiply by the molar mass of what you're making to get back up to grams. Grams, moles, ratio, moles, grams. Every mass problem, same 3 steps. Step 1. 42.0 grams of nitrogen divided by 28.02 grams per mole. Grams cancel, 1.50 moles of nitrogen. Step 2. Cross the arrow. 1.50 moles of N2 times 2 moles of ammonia per 1 mole of N2. Nitrogen cancels. 3.00 moles of ammonia. Step 3. Back up to grams. 3.00 moles of ammonia times 17.03 grams per mole. Moles cancel, 51.1 grams of ammonia. And check it, the 42 grams of nitrogen plus the 9.07 grams of hydrogen that reacted equals 51.1 grams of ammonia. Mass is conserved. It always was. But the grams only balance because you routed them through the moles. Grams, moles, ratio, moles, grams. Only moles cross the arrow. An airbag has to fill about 67 liters in roughly 40 milliseconds. It does it from a handful of powder, sodium azide, which decomposes into sodium metal and nitrogen gas. 2NaN3 makes 2 sodium plus 3 N2. So here's the question. From 130 grams of that powder, how many liters of nitrogen do you get? Here's the fact that makes gas problems easy. 1 mole of any gas at standard temperature and pressure takes up 22.4 liters. Any gas. Hydrogen, nitrogen, carbon dioxide, 2 grams, 28 grams, 44 grams. Completely different masses, exactly the same volume. Gases barely care what they are. They only care how many. And this is the whole trick. It's the same roadmap you already know. Grams to moles across the mole ratio. Nothing changes. The only difference is the last step. If the question asks for grams, you multiply by molar mass. If it asks for liters of a gas, you multiply by 22.4 liters per mole instead. Same road, different exit. So quickly, 130 grams of NaN3 divided by its molar mass, 65.01. Grams cancel, 2.000 moles. Then the ratio, straight off the coefficients, 3N2 for every 2 NaN3. 2 moles times 3 over 2, 3.000 moles of nitrogen gas. Now we're at moles of gas, and that's the fork. Last step, take the volume exit. 3.000 moles of nitrogen times 22.4 liters per mole. Moles cancel, 67.2 liters. The bag fills. 2 cautions, and they're the ones that cost points. 22.4 only works for gases, never for a solid or a liquid. And it only works at STP 0 degrees Celsius, 1 atmosphere. Anywhere else you need the gas law. Same roadmap every time. Just pick the right exit. Two videos ago I showed you this. 1 to 3 to 2 is not a gram ratio. Weigh those and you get 28, 6, and 34 grams. Nothing like 1 to 3 to 2. But watch what happens if we measure in liters of gas instead. Same reaction, same coefficients. 60 liters of hydrogen. How many liters of ammonia? This is Avogadro's law. At the same temperature and pressure, equal volumes of any two gases hold equal numbers of particles. Volume tracks the count, not the size of the molecule, not its mass. And if volume tracks the count, then a ratio of volumes is a ratio of moles. They're the same ratio. So here's the proof. Take the long way. Divide the liters by 22.4 to get moles. Apply the mole ratio, then multiply by 22.4 to get back to liters. But look, you divided by 22.4 and then multiplied by it again. It cancels. All that's left is the ratio. So for gas to gas, you can go straight across. Let's do it both ways. Short way, 60 liters of hydrogen times 2 liters of ammonia per 3 liters of hydrogen. Liters of hydrogen cancel, 40 liters of ammonia. Long way, 60 divided by 22.4 is 2.68 moles, times 2/3 is 1.79 moles, times 22.4 is 40 liters. Same answer. And the same equation tells you it used 20 liters of nitrogen to do it. Two conditions. Both substances have to be gases. A gas to a solid still goes through moles, and they have to be at the same temperature and pressure. Notice that's looser than last time. It does not have to be STP, because whatever the molar volume is, it cancels. So, the whole map. Grams to moles by molar mass. Moles across the arrow by the coefficients. Moles out to grams or to liters. And gas to gas straight across. That's stoichiometry. Here's a recipe. 2 graham crackers, 1 marshmallow, 1 square of chocolate makes 1 s'more. Now check the pantry. 20 graham crackers, 12 marshmallows, 12 chocolate squares. So how many s'mores can you build? You have more graham crackers than anything else. But the recipe eats them 2 at a time. 20 crackers only gets you 10. And after 10, the crackers are gone, the lime stops, and 2 marshmallows and 2 chocolates are left sitting there. Chemistry does exactly this, and the balanced equation is the recipe. 2 hydrogen molecules plus 1 oxygen molecule makes 2 waters. So put 10 hydrogens and 7 oxygens in a flask. Every oxygen grabs 2 hydrogens, 1, 2, 3, 4, 5, and the hydrogen is gone. 10 waters made and 2 oxygen molecules left with nothing to react with. Notice you started with more hydrogen than oxygen, and hydrogen still ran out first. The limiting reactant is not the one you have the least of, which means you can't eyeball it. Here's the method that always works. Take our old reaction, nitrogen plus 3 hydrogen makes 2 ammonia. You're given 56 grams of nitrogen and 6.05 grams of hydrogen. Convert both to moles, 2 moles of nitrogen, 3 moles of hydrogen. Now run each one all the way down the roadmap as if it were the only thing that mattered. Nitrogen says 4 moles of ammonia. Hydrogen says 2. Whichever gives you less is the one that runs out first. Hydrogen limits. 2 moles of ammonia, 34 grams. And it only ever used 1 mole of the nitrogen, so 28 grams of nitrogen never reacts at all. This is everywhere. Put a jar over a candle and the flame dies, not because the wax ran out, but because the oxygen did. Oxygen was limiting. Run an engine with too much fuel and you get the same problem, not enough oxygen to burn it cleanly, so you get soot and carbon monoxide instead of carbon dioxide. And engineers use this on purpose. In an airbag, the sodium azide is made the limiting reactant, so all of it is consumed, because leftover azide is poisonous. In a chemical plant, you flood the reactor with the cheap reactant, so the expensive one is completely used up. So, 3 steps. Moles of every reactant you were given. Run each one down to product. Smallest answer wins. That is your limiting reactant, and it alone sets your theoretical yield. Everything else is in excess, and you can work out exactly how much is left over. So add 1 question to the front of the map. Before you cross the arrow, ask which reactant is actually in charge. Put 100 popcorn kernels in the pot. Every one of them is supposed to pop. So how many do you get? 87. 13 are still sitting at the bottom, unpopped. Nothing was destroyed here. They're right there. You just didn't get what the recipe promised. 87 out of 100 is 87%. That number has a name in chemistry. It's called percent yield. There are 3 numbers here, and you have to keep them straight. Theoretical yield is what the math promises, and you calculate it from the limiting reactant, and only the limiting reactant. Actual yield is what you really scrape off the filter paper and put on a balance. You can't calculate that one. You have to measure it, and percent yield is simply the second number divided by the first, times 100. So let's finish the problem we started last time. 56 grams of nitrogen, 6.05 grams of hydrogen. Hydrogen was the limiting reactant, and it promised 34.06 grams of ammonia. That is the theoretical yield. Now you actually run it, you dry the product, you weigh it, and you get 27.2 grams. So divide. 27.2 over 34.06 times 100. 79.9%. So where did the missing 7 grams go? Not nowhere. Mass is still conserved. Some of the hydrogen simply never reacted, exactly like those unpopped kernels. Some of it went into a side reaction and made something else. Some of your product stayed stuck to the glassware or washed away when you purified it. And here's a useful tell. If you ever calculate more than 100%, you haven't broken physics. Your product is wet. Dry it and weigh it. Is wet. Dry it and weigh it again. This is why yield is money. A single pass through an industrial ammonia reactor converts only about 15%, so the plant recycles the leftover gas around and around. And in drug manufacturing, yields multiply. 5 steps at 80% each does not leave you with 80%, it leaves you 33. So, theoretical from the limiting reactant, actual from the balance. Percent is the ratio. That's percent is the ratio. That's percent yield.